In 2022, OpenAI released Whisper, which set the gold standard for local speech-to-text transcription. This was an end-to-end encoder-decoder architecture. After Whisper, NVIDIA is really leading the automatic speech recognition category with their local parakeet models. They have released both the autoregressive versions and non-autoregressive models. And these models are not only better at word error rate, but also are much faster compared to Whisper and some of their other competitors. The parakeet models are also powering an app that I'm developing. It's called Write, WHRYTE. It's one of the fastest speech-to-text transcription system for macOS that works across all of your apps. However, these models have one major limitation when it comes to streaming responses. They use something called sliding window approach or buffered inference. This way, they're able to keep context of the previous audio signal. However, the model must reread previous frames to maintain context, and as a result, as the incoming audio stream increases in duration, you're going to see much worse GPU VRAM utilization. Now, to solve this, NVIDIA just released Nemotron Speech ASR at CES 2026. It's cache-aware streaming for real-time voice. So to understand this, let's look at the problem one more time. Traditional streaming ASR uses something called buffered inference. In this case, audio is processed in a sliding window. Each window overlaps with the previous one, and the model reprocesses audio that has already seen. This is like rereading the last few pages of a book every time you turn the page. Now, this is fine for small audios, however, it breaks at scale. But why? So, same audio frames are re-encoded repeatedly, which means same attention context is recomputed at every step. This also means that the GPU memory fills with redundant activation. So for voice agents, this can be fatal. Even a few seconds of lag breaks the turn-taking capabilities of voice agents. So they proposed cache-aware streaming ASR. Now here's how the architecture actually looks like. So you only process new audio deltas, and we are using past computation instead of recalculating them every time. Now in this case, the model maintains an internal cache of encoder representation across all self-attention and convolution layers. This also means that we are processing each audio frame only once. There is no overlap. And this can result 3x higher efficiency than buffered system. Now, here's a visualization of this compared to the buffered inference. In this case, we are only processing the delta and storing the state, which carries the context forward to the next step. We are not doing any rereading. I'll show you some practical examples of this later in the video. Now, here's the pipeline. So we have the audio stream coming in, which gets chunked, then goes through cache-aware encoder with the context manager maintaining state. Then the RNN transducer decoder produces next output. In terms of the architecture, it's fast conformer with 24 encoder layers plus the RNN transducer decoder. It's based on the previous parakeet model. So again, it's a 600 million parameter model. It processes streaming audio in 16 kilohertz, but the output in this case is only English. Some of the parakeet models are now multilingual. Here is where it gets very interesting. You can dynamically control the latency mode. So at inference time, you can actually choose your operating point without any retraining, which means at the sacrifice of word error rate, you can get much higher throughput at a much lower latency. So depending on your use case, you can dynamically select these latency modes. Let's look at some performance results before we look at a couple of demos. Now, according to some of the results that they have shared, the previous parakeet models, specifically in the parakeet CTC 1.1 billion model, where CTC stands for Connectionist Temporal Classification, it's a non-autoregressive model. It could handle 180 concurrent streams. On the other hand, this new ASR model is able to handle 560 streams if you are using the same hardware with a 320 millisecond latency. Now, one thing I want to point out, the CTC model that they are using is 1.1 billion. The Nemotron ASR is 600 million parameters. However, although the size is smaller, it gives much better error rate at the word level. So they are doing a direct comparison in terms of performance, not the model size. But here's the best part. This model gives you zero latency drift even at the maximum load. The previous parakeet models would have much higher latency as the load increases. Okay, so let's look at a code example of how you would use something like this in practice. Later on, I'll show you a real-time demo as well, because this is where the new ASR model actually shines. So right now, we are using this on NVIDIA Nemo on DGX Spark. And thanks to NVIDIA for sending me the DGX Spark unit. So here we are using the Nemotron Speech Streaming ASR model. The actual transcription logic is implemented here. And then I'm collecting different statistics that is going to be presented with every transcription. Okay, so right now I'm running everything on the DGX Spark. At the moment, the GPU utilization is 0%. So we're going to transcribe this audio file, which is a 13-minute audio transcription of one of my videos. Now keep in mind, if you run the same experiment on another hardware, which is specifically designed for inference, you'll probably get much better latency. So in the first step, it loads the model. At the moment, it's transcribing is GPU utilization is about 96%. So the total load time for the model was 4 seconds. Pre-processing was around 9 seconds. The inference time was about 27 seconds, which is pretty great because it's almost 28, 29 times faster than real time. And here is the audio that it produced. Now, here's the second version that is going to fake this streaming. At the moment, I'm running this on a remote server. So it's a separate machine from the one that I am recording this video on. As a result, I cannot have real-time transcription, but that's something in the process. I'm actually trying to create a voice assistant that is going to live on DGX Spark, and I should be able to interact with it through voice. It will generate responses through voice as well. That's going to be potentially another video, so stay tuned for that. But at the moment, we're going to increase the chunk size to 2000, and let's run this. So this is going to basically chunk the audio stream, and it's going to try to mimic real-time streaming. And you can actually see that streaming the responses. Also, the GPU utilization is pretty consistent for the stream of chunks that we are creating. And even on DGX Spark, you can actually get some really good latency numbers for real-time streaming. Let me show you a quick real-time demo of how this looks like in practice. So for this, we're going to be using the Nemotron Speech ASR demo that is currently running on Hugging Face. Link to this is going to be in the video description. This is powered by NVIDIA Triton. You'll need to connect your microphone. Okay, so this is real-time transcription that is happening on this demo. So far, it does seem to be very accurate. And I think it's going to be extremely useful for real-time streaming audio applications. So do check it out. Link to this is going to be in the video description. Anyways, this was a video on the new Nemotron Speech ASR model. Do test them out if you are looking for a streaming text-to-speech system. So do check them out if you're looking for a streaming speech-to-text system. Keep in mind, it's English only at the moment. There's also a multilingual version of this on NVIDIA's roadmap. So that will be extremely useful for streaming applications. I'm looking forward to that. Anyways, I hope you found this video useful. Thanks for watching. And as always, see you in the next one.